Are you in the business of nanoparticles for nanomedicines, vaccines, synthesis, chemicals, cosmetics, food, or other applications? Is particle size one of your must-know characteristics in R&D, manufacturing, and quality control? We're In-Process LSP, and we'd like to introduce the NanoFlowSizer, a groundbreaking solution in process analytical technology. The NanoFlowSizer provides real-time inline analysis with direct nanoparticle size information to help understand and control your products and processes. The NanoFlowSizer is based on spatially resolved dynamic light scattering, the only commercially available technology capable of measuring particle size in flowing suspensions in a fully automated way. At In-Process LSP, our team has a passion for process analytical technology, and our top-class scientists are committed to delivering outstanding solutions for our customers. The NanoFlowSizer is successfully used for development and production of nanomedicines for oncology, vaccines for COVID-19, and other pharmaceutical nanoparticle-type formulations. In addition, the NanoFlowSizer technology offers great benefits in other markets, including specialty coatings, inks, chemicals, food, and cosmetics. Most importantly, there's total flexibility and modularity, so you can adapt the system to your own specific needs. In-Process LSP, innovators in process analytical technology.
Hello everyone, good afternoon and welcome at this demonstration event of In-Process LSP. We are here in the lab of In-Process LSP, and I want to introduce you to the team that will handle the demonstrations today. I'm Aggregation, I'm Managing Director of In-Process LSP, and I'm working today with Raquel and with Remy. So Raquel, maybe you can say a few words for introduction yourself.
So I'm Raquel, I'm Application Specialist at In-Process LSP, and I'm mainly in charge of helping the customers with some feasibility studies. And today I will show you how the NanoFlowSizer works, and I will also show you some experiments.
Okay, thank you very much. And Remy?
Hi, I'm Remy. Last year we did research upon coupling a high-pressure homogenization upon the NanoFlowSizer. I worked with that, been experienced. I will show you the application later on.
Okay, thanks very much. So in a minute we will start with our demonstration. First we will explain you a bit more about the technology backgrounds in slides, and after the slides you will have live feed videos available, and I hope it is really informative for you. So enjoy and let's see what comes.
We will start now explaining more details and background of spatially resolved dynamic light scattering. Spatially resolved dynamic light scattering is one of the PAT technologies within the PAT4Nano consortium being further developed and explored for different applications related to nanoparticle formulations and processes. Before going into more detail of the technology, we may consider why PAT or process analytical technology is so important and how we can benefit from PAT in general. Process analytical solutions provide valuable insight in processes and increase process and product understanding, which help to speed up development and validation activities, as well as supporting continuous improvement. Secondly, for process scale-up and transfer, PAT provides opportunities to monitor critical aspects of the process. For commercial manufacturing, full process control, including continuous and real-time measurements, feedback and feed-forward loops can be applied to assure consistent and optimal quality of the end product. A third and more straightforward beneficial area in which PAT provides direct savings and efficiency is related to elimination of sampling procedures and offline analysis. Sampling and offline analysis take time and manpower. In addition, processes may not continue during offline analysis, which affects capacity and efficiency of manufacturing directly. Sampling itself may also introduce various risks related to representativity of the sample or sterility of the process. Conventional dynamic light scattering technologies show limitations to be used as PAT tool. Therefore, new and other approaches are required. Conventional dynamic light scattering analysis cannot handle turbid nanosuspensions without dilution, which makes the technology unsuitable for direct measurements in most nanoparticle processes. Secondly, conventional dynamic light scattering requires a static or non-flowing sample for adequate measurements. This is clearly not the case for most processes. Besides limitations on turbidity and flow, the speed of analysis is also important for PAT. Monitoring fast-changing properties and applying real-time process control demands analysis times closer to seconds than minutes. Also, flexibility to connect a technology to a process, either to small-scale R&D situations or full-size manufacturing configurations, is of importance for flexibility of the technology. As a last requirement, any PAT solution should preferably not require extensive method development for each product or situation. Spatially resolved dynamic light scattering overcomes these limitations and is therefore very applicable as PAT tool. As we will see in the next slides, the technology is able to measure highly turbid samples, measure nanosuspensions in flow, and to measure at frequencies of 5 to 10 seconds. Flexibility for different scales and types of processes is also addressed, as we will see later. Furthermore, for most applications, no additional method development or calibration is required. Besides the DLS type measurement, spatially resolved diffusion wave spectroscopy is an alternative approach which is under development within the PAD4Nano consortium as well. For the DWS type measurement, the same technology is applied, but data processing is solely based on multiple scattering. This becomes particularly useful for extremely highly concentrated nanosuspensions, as often seen in nanomilling applications. The DLS type measurement provides particle size information similar as for conventional dynamic light scattering, while the DWS type measurements provide an average particle size only. For today's demonstration, we will focus on the DLS type measurement only. Conventional DLS is based on interaction of laser light with nanoparticles, resulting in intensity fluctuations due to interference of moving nanoparticles. The Brownian motion of the nanoparticles, or diffusion rate, relates directly to the size of the nanoparticles. Smaller particles diffuse faster and result in intensity fluctuations at higher frequencies. The obtained intensity fluctuation, or scatter pattern, is further processed into a decorrelation function. The faster the decorrelation, the faster the diffusion rate and the smaller the particles. Based on the steepness and shape of the decorrelation, a particle size distribution can be obtained. For spatially resolved DLS, instead of one, about 1000 scatter patterns are obtained simultaneously as function of depth or path length. This is possible since spatially resolved DLS applies a broadband light source containing multiple wavelengths instead of a single wavelength. The obtained backscatter signal of the broadband source enters an interferometer, which enables to distinguish between scatter signals coming from different path lengths in the sample. This principle is called low coherence interferometry. Once scatter patterns are obtained as function of depth, up to about 3 mm in the sample, decorrelation functions of each scatter pattern are subsequently processed and translated into particle size according to the Stokes-Einstein equation. Now we have a closer look why the spatially resolved data helps to measure higher turbidity levels. In DLS, only scatter patterns obtained by single scattered light will result in an accurate particle size. The higher the concentration of particles, the higher the chance that the light is scattered more than once. This is called multiple scattering, and this should be avoided in conventional DLS. The spatially resolved data contains scatter patterns and decorrelation data as function of depth. Deeper in the sample, the chance for multiple scattering increases. For smaller path lengths, single scattering data may still be present, even for highly turbid samples. By isolation of the single scatter data only, particle size and distribution can be obtained. The isolation of single scatter data is automatically performed by the algorithms in the software. In the lower panel, the applicable range for particle size measurements in undiluted samples is shown. Since turbidity is dependent on concentration and particle size as well, both have to be taken into account. In this example for polystyrene, it can be seen that above the dashed line an accessible area of higher concentrations and particle sizes have become available. Based on optical properties of the nanosuspension, this figure may change, although the accessible area for spatially resolved DLS will always be larger compared to other DLS type technologies. Once we are able to measure highly turbid samples and concentrated samples, we also have to take into account possible interactions of nanoparticles, since they may affect the diffusion rate and therefore the accuracy of the obtained particle size. This table shows how spatially resolved DLS can be applied for different situations related to concentration or volume fractions of the nanosuspension. In the first row, representing a nanosuspension with a relative low volume fraction of particles, diffusion rates of particles are not expected to be influenced by interactions. Therefore, the spatially resolved DLS measurement can be applied directly and accurate particle size information is directly obtained. By increasing the concentration or volume fraction, particles may start seeing each other. For volume fractions well above 5%, this is often the case. Interactions may hinder the diffusion of particles, resulting in often overestimated particle size. By evaluating particle size measurements of dilution series, this effect can be measured and corrected for. Worthwhile to mention, for process control, even hindered diffusion data may already be sufficient to control a process. The diffusion rate is measured in all cases adequately. We have now seen the ability of spatially resolved DLS to measure higher turbidity ranges. Besides turbidity, the technology has also to manage flow of nanosuspensions as we want to measure during processing. As can be seen in the upper left panel, flow as an additional movement of particles increases the decorrelation and therefore steepness of the decorrelation functions. For laminary flow situations, the contribution of flow follows a Poisson type relation, which can be corrected for by specific fitting algorithms. The diffusion rate of the particles without contribution of flow is then used for further processing into particle size data. In the middle panel, you can see accurate particle size information based on different flow rates. In order to be able to apply such a flow correction, the spatially resolved flow profile is measured for each measurement, as can be seen in the right upper panel. This flow correction can be applied up to relatively high flow rates, up to about 300 liters per hour. Less than 2% variation in particle size is observed. For higher flow rates, turbulence may become present and will negatively affect the flow correction process. Finally, at the end of this introduction, I will summarize the most important characteristics of spatially resolved dynamic light scattering. It is based on the same principles as conventional dynamic light scattering, although it uses other hardware, a broadband light source, and interferometry. Spatially resolved DLS obtains about 1000 scatter patterns as function of depth simultaneously within 5 to 10 seconds. Spatially resolved DLS can measure highly concentrated or turbid samples in a static or flowing condition. For high volume fractions and concentrations, the influence of possible particle-particle interactions should be evaluated, since interactions may affect the diffusion rate of particles and therefore particle size calculations. And with this information, we will go into the lab and see how the system works. Hello, welcome again. We just entered here the lab of in-process LSP, and in front of us is the NanoFlowSizer. As discussed in the introduction about the technology, we will have now a closer look to the system itself, and Raquel will explain the different units of the system in more detail, and we can discuss the system for static measurements.
Yeah. Okay, so as you have seen in the slides, the NanoFlowSizer is composed by a base unit, that is this one, that contains the light source and the detector. Then here we have the probe unit that has the interferometer. So the base unit is connected to the probe unit and also to this computer, that is one that we deliver with the NanoFlowSizer, because it's able to process 1 GB per second. Okay, so here, as you can see, we have the probe unit, and we can attach different models. This one is the static model, in which you can attach a vial and perform static measurements.
Okay. So maybe sort of a stupid question, but we are here in a PAT environment. We are talking about inline measurements.
Yeah.
This is a module, a sample module to take measurements of vials.
Yeah.
Why is that also important?
So this is important, first of all, to check that everything is fine. So normally we put a reference, that is the one that I'm gonna measure later, to check that everything works fine and that you get the particle size that we expect. But also for at-line measurements. So if you are in a process and you want to take samples and check the particle size, you can do it with this
But you
model.
are meaning at-line then?
Yeah, at-line.
Okay. Yeah, just to be sure. But
Yeah.
it means, in fact, that possible users, they take samples, still samples from their process.
Yeah.
So it's not really PAT.
Yeah,
But
you
in
can still...
in an at-line situation, they will take samples of their vials
Yeah.
in a rather fast way.
Yeah, exactly.
Okay. Yeah. Yeah.
Yeah.
Okay.
Yeah, sometimes we also have high turbid suspensions in which we see hinder diffusion. So we use this static model to do dilution steps and check if we have hinder diffusion or not.
Okay. So also for evaluation of the properties of the suspension and how it behaves with our measurements and to optimize settings, it's really effective to use the vial module instead of directly in-flow measurements.
Yeah, exactly.
Yeah. Okay.
And also for monitoring a process, so for example for crystallization, that I will explain later, you can do the experiment here and you can see at real time how the particle size is changing.
Okay. So first of all, the static module is always used in the system to take a reference and to check performance of the system.
Yeah.
So it might be good to have a go and have a look at it, how it works.
Okay, so first of all, we have to create a new project. And then we go to data acquisition and we initialize the NanoFlowSizer.
Okay, so at this stage the software is connecting to the system in the communication and checking whether...
Yeah, here we can see that it's initializing the base unit. So now we can see that everything went fine and we have a tick here. So now we go down and we check the signal.
So first it's about communication with the hardware, and now it's more about the signal. Okay.
Yeah.
And here we see some, well, panels with information in there.
Yeah.
Yeah.
So here we can see different panels. So the first one you can see where the edge, the intensity, and the focus is of the sample, that we can control with this panel here. And here in the raw intensity, we can visually see our vial. So here we can see the edge of the vial where the glass is. And then when we start seeing the colors from yellow, red, is where the particles are. So we can see some intensity there due to the presence of particles.
So if I'm correct, the axis here, if you go down in this panel, you are going deeper in the sample, and this is the edge of the glass.
Yeah.
Okay, and it's important apparently to focus and to set the system quite well. Of course, after the glass focus, otherwise you're not measuring in the sample.
Yeah, exactly.
And those settings are of course important to get the optimal signal.
Yeah, exactly.
Yeah. Okay.
And it's important to focus close to the glass of the vial because that's the place where normally we have single scattering.
Yeah, okay. And these settings, if you actually can change them as you say here in focus, path length and intensity, I suppose these are mostly related to the properties of the suspension,
Yeah.
the turbidity of the suspension, and maybe even the particle size or other characteristics. But these settings, if you change them, they are automatically adjusted in the probe unit electronically by servo engines or by
yeah. So there are some motors in the probe unit. So with those motors, you can change the focus and the path length. So normally, we press home, we go to the latest value that was used for this model. So we can do that, and we can see that now there is some noise in the probe unit because the motors are moving. And we can see some changes here. So the NanoFlowSizer is able to detect the model, and normally all the settings are already in place.
Okay, so that's of course if you change those modules to different modules, it actually remembers or identifies the module, and then it corresponds to the settings of the engines to set the focus well.
Yeah, exactly.
But it could be different if you start measuring other samples. So you also should be able to adjust it and to check it before you actually go into your application. Okay.
So for example, this sample has a low turbidity. So we see an error in the reference intensity that is a bit low. So we should change the reference intensity here because of the characteristics of this sample.
Okay.
But as we can see, after changing the focus, we went back to the previous position, and everything looks fine regarding to the focus. So now I'm going to change the reference intensity. So as you can see that if I change the value here, we are going to see an increase in the reference intensity value.
Okay. And what you are typically looking for in these panels before you say, okay, the settings are okay, is that it should be a stable picture, or should this one always be higher than the other one? Or
so you should have a value that you can check here. So here you can see a bit of explanation also about the system and the values recommended for the focus, the reference intensity, and the path length. So here you can see some information. So for example, for the focus, you need around 125 pixels to have a proper measurement. For the path length, 30 pixels, and the reference intensity should be between 0.2 and 0.5. So that's the value that we are looking for.
Okay, very good. And this information is in the help function in the software.
So if you forget about that, you can check there.
Yeah. Nice. And do you actually have to do this tuning for every measurement?
Normally, if you are using the same model and the characteristics of the samples are fine, you just have to check once and then everything will run fine.
Okay.
But it's good also to check this panel here. So now I modify the reference intensity, and it's inside the values, that is between 0.2 and 0.5.
Yeah.
So we can see that everything is tick. So in principle, we can do a measurement.
Okay, very nice. Okay, good.
Okay, so now I'm going to press OK, and all the settings will be safe. So now I'm going to go to Main Menu and Project Settings. So here you have to put some information about the samples and acquisition settings and analysis settings. So here I'm going to put the batch code of the sample. In this case, it's a reference of polystyrene that has a particle size of 100 nanometers. So here you can modify some analysis settings, such as the analysis mode, the type of solvent. You also have the option to measure the temperature, as the model has a temperature sensor, but you can also set the temperature manually. So now what I'm going to do is to select the static analysis mode. So in this panel, we have to fill in some information for the modeling of the particle size distribution. So the more we know about our sample, the better it will be for the fitting. So we have to fill the minimum and the maximum particle size if we know it. And also if we know how polydispersed our sample is, we can also modify the lambda and the fit limit, that are some parameters that are used for the fitting and smoothing of the particle size distribution. So finally we can go to storage settings. So here we just have to select the folder where you want to store all the data files. And that is all. So now we are going to perform a measurement. So for that we go to main menu, data acquisition, we press start. Okay, and now we just have to wait to get some data points. So here in the table at the top left, we have some information of the particle size, including the set average and information about the particle size distribution. Then in the graph at the bottom left, we have the correlation functions at different path lengths. So as it was explained during the introduction, as we are using a spatially resolved technology, we are able to have information at different path lengths. So finally, in the graph at the top right of the panel, we can see the particle size distribution and the PDI at real time. And at the bottom of the slide, we can also have information of the particle size distribution for each time point. So now what I'm going to do is to take the vial out of the NanoFlowSizer and see what happens. So I'm going to take the vial out, and now we can see that there are no decorrelation functions anymore, and the signal disappears completely. And also, if we look at the bottom of the panel, we will get an error message saying that there is no data. So what I'm going to do now is to put the vial back and see if we get the signal back. So we are going to wait for a few seconds. And now we can see that the decorrelation functions are back, and that again we obtain a particle size of around 100. So the set average is around 98 nanometers, that is within the limits of the reference. So up to here we have seen the instrument, the settings, and an explanation on how everything works. But in the next experiments we will show more in depth some experiments where you can get particle size information at real time.
So, we already saw some measurements with the system. We talked in the introduction about hindered diffusion, what we called hindered diffusion, which is related to the concentration and the loading of particles in a way that they start seeing each other and that it might interfere the diffusion rate. Yep. And therefore also the particle size that you actually extract out of the measurements. Yeah, exactly. So in this demonstration you want to show an undiluted sample as such, because for PAT of course we need to do the measurements in an undiluted way. Yep. So first of all you want to see whether it's possible to do that in an undiluted sample. Yep. Of course many technologies can actually not do it, but interesting to see is what is the effect of hindered diffusion. Is there an effect? Yeah. And if I'm correct, we can say something about hindered diffusion if a diluted sample has a different particle size outcome than the undiluted sample. Yeah. Yeah? Yeah. Okay, so take us on.
Yeah, I'm going to analyze this emulsion, that is a soybean oil emulsion that is suspended in water. So I will first measure the as received sample as it is in the bottle, and then I will do dilution 1 in 2, 1 in 10, and 1 in 100 to see if there is any change in the particle size.
And in principle, in the most diluted sample, you would expect that the interaction between particles is, let's say, totally neglected or not present anymore.
Exactly.
So that would be, let's say, the sample which refers to the not hindered diffusion always. Huh?
So in the case of the as received, as particles are very close together and they are interacting, they diffuse slower, so we are expecting to see a bigger particle size.
Okay.
Yeah.
So you can already see that it's quite turbid. It's a relative high concentration of high concentrated emulsion.
Yes.
It is a bit milky. And in the other vials you have already entered a bit of water.
Exactly.
As a diluent.
Yeah, so I'm using water to dilute the samples. So I already added the water. Now I just have to add the emulsion.
I think we know also by experience that sometimes if you dilute, that the dilution medium can also be important. That you don't want to initiate agglomeration or other effects by the dilution itself. Maybe pH changes or viscosity changes even is also important.
Yeah.
So you have to take care.
Yeah.
But in this case, the water diluent will work.
Yeah. So in this case, the samples are, so the droplets are suspended in water, so that's the main diluent. So we are using also water to dilute.
Yeah.
So first I'm going to measure the as received sample. I need to check that the intensity is fine, and we can see that at the moment it's a bit low. Now everything is fine, so we have all the ticks, and we can start performing the experiment.
Yeah.
So here we have the first measurement. We can see that it measures fine, so we have the green line here saying that the measuring is fine. And now I want to check if there is multiple scattering in this sample because it's quite concentrated. So we can check this in this graph in the top right. So normally when there is a line at 1, it means that there is no multiple scattering. So this is the size variation as a function of the path length. So when multiple scattering occurs, there is a decrease in the size variation going lower than 1. So in those cases, the NanoFlowSizer will filter the information of single scattering and it will do the processing with that data. But we can see that this sample is fine. We have single scattering, so now it's measuring fine.
Yeah.
So in principle, this sample can be measured.
But even if it was multiple scattering for, let's say, at a certain depth, it was not a problem for the analysis.
No.
Okay. Yeah.
Okay, so at the moment we are having a zeta average of 300 for the undiluted sample.
Yeah. And there is a bit of polydispersity. You see in the particle size distribution also a bit of really small particles in there.
Yeah.
And I guess the formulation that we used, it was not too surprising that it's not fully monodispersed.
Exactly.
So that's nice to see.
Yeah.
But I think main piece of information that we are looking at 300 nanometers as in the undiluted sample. So we would expect slightly different particle size if there is hindered diffusion of these particles if we have a look at the dilutions.
Exactly.
Okay.
Yeah.
Well.
So now we are going to check one of the diluted samples.
Yeah, so we keep in mind 300.
300, and then I'm going to measure dilution 1 in 2. Okay, we can see now that, again, everything is fine in the measurement. We have the green line there, but the set average has decreased. So now it's 264 instead of 300.
Okay. And the logic indeed behind it would be if the particles start seeing each other and the diffusion rate is slower, that by the slower diffusion rate we would translate that to larger particles.
Exactly.
So in the undiluted sample you would expect larger particles, and indeed you see here around 270, about 10% lower.
Yeah.
Okay. So if you evaluate your sample or your formulation, because this is a typical concentration dependent thing, you actually have to evaluate at what's the real particle size. So you have to dilute until you don't see any changes in particle size anymore. Okay.
So what are we gonna do after measuring all the sample is plotting the particle size as a function of the concentration. So we normally see a line, and at some point there is a place where the particle size is stable.
Okay.
So we can be sure that at that point there is no hinder diffusion anymore.
Okay. Okay. And in the end, it would be for the user if you have systems, let's say in PAT, in a process where you have differences in turbidity or in concentration, like growth of particles or whatever, then this type of hinder diffusion factor can actually build in the system, in the software, and by sort of, let's say, backscatter intensity, you can also say something about the concentration.
Yeah, exactly.
Okay. So it can correct.
It can be corrected
for those situations, but also a little bit dependent on the formulation and how complex the hinder diffusion is.
So you have to do some measurements before knowing your sample, and then in principle it can be corrected.
Okay.
Okay, so now I'm going to measure dilution 1 in 10. Dilution 1 in 10 is similar to the previous one, so it's 253. So maybe at this point we can already see that the hinder diffusion is lower than before.
Yeah. So it's I think it was 260 something, and now it's 250 something. So there is a small effect still. But around 250, if we have a look at the 100 times diluted sample, you would expect a similar particle size in this. And you can also see that the dilution itself is probably also having some impact on the polydispersity. Because at higher dilutions, the let's say the small particles that we measured in the undiluted samples are actually disappearing.
So you cannot see them anymore.
Something to consider if you dilute, that you also might change the formulation of the sample in a way.
So now I will measure the last sample, that is dilution 1 in 100. So again, you can see that the set average is around 160, the same as in the previous one. So we can be sure that in the previous measurement and in this one there is no hinder diffusion anymore.
In principle it's exactly 250 something, that's exactly the same as before. Okay, clear. Thank you.
You're welcome. So in this chapter 4, I will give you an introduction on how the NanoFlowSizer works in the presence of flow, and the requirements and specifications needed to be able to have proper results. So how are we able to measure in the presence of flow? The first requirement for proper results is to have laminar flow. So as we can see in the top image, it is important that during the measurement the sample is in the fully developed region, and thus the flow profile can be calculated and fitted as a parabolic fit. If we look at the picture at the bottom of the slide, this one, we can see different particles at different positions in a pipe that are subjected to laminar flow. So the particles close to the wall are mainly moving due to Brownian motion, but the deeper we go into the sample, the stronger the flow component is. So we spatially resolve DLS. Information at different depths is originated, and the points in which the flow component is strong are filtered out, and with the remaining data and using smart algorithms, the component of the flow is subtracted, and information of the movement of the particles due to Brownian motion is taken into account for the calculation of the particle size. So to ensure laminar flow, we have developed different flow models, and the things that are important to take into account are the diameter of these flow cells and also the length. So the faster the flow rate is, the bigger the diameter of the flow cell must be. So for this reason, we have developed different models to ensure laminar flow for the different flow rates. In this way, with our biggest flow cell, we can go to flow rates up to 300 liters per hour. Secondly, as I explained in the previous slide, we need to have long flow cells to overcome the hydrodynamic entrance region. So for this reason, all of our flow cells are quite long, as you can see in the picture, and I will show you later in the lab, to ensure that at the measuring point, the flow is fully developed. In some cases, due to specifications in the process, flow rates that are higher than our maximum limit are needed. So in those cases, we recommend to design an online loop, and then you can choose the flow rate and the flow cell that you want during the measurement. Another thing that is important to take into account is the pump that you use. So to avoid pulsation and to have proper data, we recommend to use a microgear pump as the one shown in this slide. So there are some specifications of flow limits that can be used depending on the flow model and the particle size of the particles that need to be measured. So the limits are based on laminar flow requirements, but also on the time needed for the particles to be measured. So as big particles need more time to be measured, the flow rate applied in the cases that these big particles are present need to be slower when using smaller flow cells. So here we have a table in which different flow cells are recommended depending on the flow rate that you are going to apply and also on the particle size that you are going to measure. So for flow measurements, there are different configurations that we can use. So the most common one is the inline configuration, in which the NanoFlowSizer is implemented inline in your process. Sometimes due to high flow rates, as I explained in the previous slide, an online loop is required. Additionally, for processes that occur in a vessel, we can also design some online loops. The first one, the suspension goes back to the vessel, but we can also design one online loop with drain in which the suspension is discarded after the measurement. So during the demonstration in the lab, I will show some measurements in which a suspension of silica particles is measured at different flow rates using an inline configuration. But in this slide, I also want to show you the possibility of performing measurements in a stir flask. So in this case, silica nanoparticles were synthesized using a Stover reaction in a stir flask, and the growth of particles was tracked over time. So we can see in the first graph that the particle size and the PDI is measured at different time points, and we can see that the first point, due to low turbidity, they couldn't be measured properly, but after a few seconds we started to see particles, how these particles grow over time. Additionally, in this second graph, we can see the particle size distribution at different time points, seeing that over time the particle size becomes bigger and the particle size distribution broader. This means that the population of particles present at the end of the synthesis is quite broad, going from 150 nanometers to 600 nanometers. So with this example, I want to say that you can also perform experiments with some movement using a stir flask and having proper results. But now we are going to move to the lab, in which I will show some measurements performed using our inline configuration.
Hello again, and thanks Raquel for the explanation about flow and about the Laminary flow, which is really important. I think now we have time to explain a little bit more about the sample modules, the interchangeable sample modules, and the flow cells.
Yeah.
So please go ahead.
Yeah, so these are some of the flow cells that we have. So this is the smallest one, that is the micro flow cell. So I can open it and you can see how it looks like inside. So it has this cuvette that is quite small. So in case you have a low quantity of suspension, you can use this flow cell to check that the suspension is going to work in the presence of flow.
Okay.
Then we have this one that is the 1/2 inch. That is the one that I'm going to use for the experiments that I will do later. And this is the biggest flow cell, that is the 2-inch flow cell. In between this one, that is the 1/2 inch and the 2-inch, we also have the 3/4 and the 1.5 inch.
And if I understood correctly, the dimensions of the flow cells are most important related to flow rates of the process that you are applying.
Yeah.
Okay.
So you can see that all the flow cells are quite long. So it's important that you have the flow going from this side to this side, because the measurement is going to be performed here. So in this way, you ensure that there is laminar flow at the point that you are measuring.
Okay. Nice.
So if you want, I can show you how to change the flow cell. So now we have the static model attached. We have these 2 screws here.
So this also actually means that with this one system, either if you work in a, let's say, R&D environment or have to move to a pilot plant or whatever, that by changing these modules, you can actually connect to the process in larger or small scale or static or whatever.
Yeah, exactly. You can see it's quite easily to interchange them.
And the software would actually recognize again what flow cell or what module is connected.
Yeah, exactly.
And, adjust the settings.
Yeah. So now the flow cell is attached. I just have to set up the rest of the components and put the pump, and then we can perform the measurement.
Okay, and then you will see if you change the flow rates,
Yeah.
whether the signal stays constant, because that would be, of course, proof that the flow correction will actually work.
Exactly.
And that is, of course, extremely important if you are doing your inline analysis.
Yep.
Okay.
I see you have prepared the configuration to do the flow experiments, the probe unit with the flow cell connected to it.
Yep.
And we see here a pump, and this is most likely a special pump that has a pulse-free flow.
Exactly. Some micro gear pump. So with this kind of pumps, we ensure that there is no pulsation. So then we can perform a proper measurement.
Yeah. Okay, nice. So what do you want to show us?
So we have here a suspension of silica that has particles around 100 nanometers. So this is the reservoir with the solution, and the solution goes through the pump, and then goes into the flow cell. So we can see that this is the inlet of the flow cell, and the solution goes this way and is measured at this point. So what I'm going to do now is, first I'm going to perform an experiment without any flow to see what is the particle size, and then I'm going to start increasing the RPM of the pump.
And I believe what we want to see is, of course, that the particle size information is similar and stable for different settings of the flow.
Yeah, exactly.
Okay, I see the pump setting is 300 RPM.
Yeah.
To what kind of volume per timing does that correspond?
So it's between 80 and 90 milliliters per minute.
Okay.
So we can see here in the graph that we have increased the flow, but the particle size stays stable and is 100 nanometers. That is the value that we were expecting.
Yeah.
So I'm going to increase the flow a bit more. I'm going to go to 400 now.
Actually, in this screen you cannot see very much. You see some variation in the correlation functions, if I'm correct, that they are a bit more bended.
Yeah, now the particles are moving faster, so the slope is more pronounced. But we can have more information about the flow profile in advanced options. If we go to this tab, we can see here in the graph at the bottom left the velocity as a function of the path length, and you can see that in this region where it's very close to the wall there is a linear flow profile.
Okay.
And here you can also see in the top right graph the shear rate and the temperature.
Okay.
So I will increase.
And these increases in shear rate here in this panel is since we added flow starting from a static measurement going into flow. Yeah.
Exactly. So the three first measurements were done in the absence of flow, so the shear rate was 0. But then we can see that after the third measurement, the shear rate increased because we increased the flow rate. So now I'm going to go to 500. So we can see that the shear rate is slightly increasing and also the velocity profile.
Yeah. And at a certain stage, well, the flow rates are, let's say, too fast.
Yeah.
But what are, let's say, the limiting factors? What is happening at that stage?
The most important thing is that we have laminar flow, but there is a point in which we will start having turbulent flow. And for those cases, we will have a warning in the software that it will tell you that the flow rate is higher than it's supposed to be. So if you want, I can put the pump to the maximum speed and we can see what happens.
Yeah, you can just find out where we see this turbulence occur. Okay.
So now we are at the maximum. So we can see that there is a warning here saying high flow rate, and we can also see an increase in the shear rate. So this means that the flow is quite high, and now we can see also a decrease in the particle size.
So at this point the flow correction does not work correctly, and you can see it in the, let's say, the main panel here also in the measurements to be crossed or let's say marked like not reliable. Yeah.
Exactly.
Okay.
But if we go back again to 500 RPM, the shear rate is going to decrease, and also the velocity profile. And again, we go back to a good measurement, and we will start having the proper particle size results.
Yeah. Okay. And once you use the flow cells with the larger dimensions,
Yep.
we can actually move the flow rate up to, let's say, between 300 and 400 liters per hour.
Yeah.
But it might also be dependent on, let's say, the particle size or the properties of the suspension itself.
Yeah, exactly. So we have a table in which, depending on the type of material that you have, so the particle size and the flow rate that you want to use, we will indicate the flow cell that you have to use.
Yeah. So in that case, I think it's also good to mention that if for a certain process, the possibility exists to make an online loop with a very nicely defined pulse-free flow, it might show, let's say, more robust or better results compared to a process where there's lots of variation in pulsation and flow rate's not really the issue, unless flow rates are, let's say,
really high.
Extremely high.
Yeah.
Okay. So I think for possible applications, it's useful to think if an online loop is possible. It might really work well in all situations.
Yeah, exactly.
Okay. Okay, thanks a lot. We will see later on with the connection to the process instrument how it actually works in an inline situation.
Yeah.
So curious to see that as well.
Okay.
Okay, thank you. In this session, we will focus on integration of the spatially resolved dynamic light scattering technology in the process. As we have seen before, the technology is able to measure turbid samples in flow in a really fast manner. In this session, we will focus on the flexible geometry for different scales and for different purposes, different applications. The instrumentation for spatially resolved dynamic light scattering, the NanoFlowSizer, is based on a base unit containing the spectrometer and detector, and a probe unit containing the optics and the interferometer. Sample modules at different sizes and for flow, either or static measurements can be connected to the probe unit in an easy way. The sample modules contain sensors for temperature and also for identification. This is automatically managed within the software. All sample modules are based on pharma-grade materials and ensure non-invasive measurements. Non-invasive measurements for many processes is also an important factor. By using different scales and different dimensions of flow cells, the instrument can be connected either to small-scale R&D setups up to commercial manufacturing configurations. When we think about process configurations, we can think of the online configuration or an inline configuration. Most of the time, an inline configuration would be the ultimate PAT solution, since we have no diversion of the sample stream and we have a direct measurement of the process. An online configuration may help to assure laminary flow or certain conditions which may not be applicable in the inline configuration. It is also possible to use the system connected to a vessel, either directly to a vessel if flow or no turbulence in the vessel or the solution exists, or with an online loop to a vessel. Before we connect the technology to a certain process, we have to evaluate the feasibility of the application. In this slide, you see different important parameter relations in order to assess the feasibility of the application. As we have seen before, turbidity and particle size characteristics like body dispersity or size and concentration are important to assess feasibility of the measurement itself, but also the flow pattern, the shear rate, viscosity and temperature have to be taken into account. All these variables are interconnected to each other and will in the end evaluate whether the application is feasible or not. In this example, we are looking at particle growth in a glass vial. In this situation, there is no flow, and it is a very simple setup of the instrument. Particle growth in this situation is relatively fast, so it also requires relatively fast acquisition times. In the movie that I will start in a few seconds, you will see in real time how the particles start growing. For demonstration purposes, the timescale was a bit accelerated, so keep in mind that every data point in real time takes about 5 to 6 seconds. Starting point is about 400 nanometers of these particles, and as you can see, after about 150 seconds, it is above 1 micron, and particles keep growing, and the technology is still able to measure the adequate particle size, although officially we recommend to measure particle size up to 1 micron. But in certain situations, the technology can be applicable for larger particles as well. And using this type of analysis, it is very easy to study mechanisms of particle growth in real time. In this example, we are also looking at particle growth, but now part of a titanium dioxide synthesis. In the setup, as shown in the picture, you can see a probe unit connected to a microflow cell, which is the smallest volume flow cell available, and very applicable for R&D type setups for small volumes. The round bottom flask containing the reaction mixture is circulated through the microflow cell for continuous measurements of particle size. By variation of the salt concentration in the reaction mixture, different particle sizes are obtained, as you can see in the middle panel. The growing curve of the particles is adequately monitored and very detailed, given by the technology. This gives rapid insight in growth of processes and relevant process variables, and the possibility for controlled addition or tuning or stopping growth in any process. Besides the small scale application, the same principle can also be applied for larger applications. In this picture, in our lab, you can actually see the largest flow cell available, which is a 2-inch setup and capable of handling flow rates up to 300 liters per hour. In the vessel, in the front of the picture, you can see a milky suspension, which is a similar reaction vessel as in the previous small scale setup, but now simply at a larger scale. On the right panel, you can also see the distribution, the particle size distribution, how it evolves over time, starting with smaller particles and growing particles, resulting in a shift to the right side to larger diameters of the particles. It is also possible to measure droplet size of nano emulsions. In this setup, a high pressure homogenization unit is coupled to a NanoFlowSizer. As you can see in the lower panels, the droplet size decreases from above 500 nanometers to 300 nanometers in time. This is due to a pressure increase in the homogenization unit from 400 to 800 bars. On the right lower side, you can also see the particle size distribution, how it evolves in time. The more polydispersed distributions at the beginning of the process, at the start of the process, end up with more monodispersed, smaller droplets at the end of the process. For this type of configurations, it is important to evaluate the exact location of the NanoFlowSizer. If the NanoFlowSizer is connected directly to the outlet of the process equipment, you might see pulsation in flow due to the process equipment itself. In order to avoid that, it is also possible to connect the NanoFlowSizer after a vessel with a separate pump to avoid any pulsation and to perform better measurements. In this example, droplet size of a nano emulsion is monitored continuously at larger scale. As you can see, the larger flow cell here 2" is able to handle flow rates up to 250 liters per hour in this case. Typical for this type of nano-emulsion is the instability of the droplets, when shear forces are not present and flow is not applied. In order to study the effect of no flow and absence of shear forces, the flow in this process was stopped deliberately to monitor the growth of the droplets. As you can see in the middle panel, where no flow is indicated, you can see an increase in droplet size very rapidly from about 200 nanometers to above 300 nanometers in only a few minutes. This type of emulsions, unstable emulsions, makes it also very difficult to do offline sampling and offline analysis. Therefore, the real-time analysis is a good solution for monitoring droplet sizes in this type of processes and this type of formulations. Although the diffusing ray spectroscopy option is not part of this demonstration, it is also good to mention that for the DWS application, also integration with, for instance, nanomilling equipment is possible. This is a picture of a configuration in our laboratories where nanomilling applications are studied in more detail and applications are developed. This is typically for extremely highly concentrated nanosuspensions, and we will update you later with the results. The ultimate goal of PAT would not only be monitoring particle size in real time of the process, but also using that information as direct feedback or feed-forward control for the process itself. In this example, a state-of-the-art liposome manufacturing unit was integrated with the NanoFlowSizer system for direct and real-time feedback of particle size. Liposomes, which are manufactured in this system, can be controlled, the size can be controlled by the flow rate of the water addition. By having direct feedback of the particle size in the process, the flow rate can be adjusted, as you can see in the panel below. By adjusting the flow rate, the target particle size is in this case reached after about 12 minutes. And with this nice example of real PAT, I want to end this session.
Hello again, we are here again on the lab, and as we explained in the slides about connections to different processes, one of the processes that we use a lot for our experiments and also to connect the NanoFlowSizer to it is in high pressure homogenizer. Remy has lots of experience with that system and also with the coupling to the NanoFlowSizer. So he will tell us about this setup a bit more detail. So Remy?
Well, in this case we have a sunflower in water emulsion with twin as a surfactant, twin 20. We will pump it past the NanoFlowSizer, in which we will measure the average size of the batch.
And the pump, if I can, that's typically here a pulse-free pump.
Yeah, this is a micro gear pump. It's a pulse-free pump. That's the easiest way to pump it past the NanoFlowSizer. It will go into the hopper for the high pressure homogenizer, after which it will be led back into the vat. So we get a batch reduction size.
And then the entire emulsion is circulated, and by the pressure change or the settings in the high pressure homogenizer, you can actually manage to make a smaller particles or droplets, I should say, in time after a number of circulations.
Yeah, depending on the number of passes and the pressure in which the homogenizer is set at that point, the droplet size will be.
Okay. So you will make some preparations for the system, and then we will actually launch the process. So we will have that catched on video as well for the attendants to see. So, I would say if you prepare the instrument, we can have a look how the process is doing and how particles become smaller or droplets during the process. Okay, thanks a lot.
So during our introduction, you have seen the measurement of a reference sample in which the particle size was staying stable over time. But now I want to show you some experiments that you can perform using the BIAL model, in which you can have real-time information about your process. So in this chapter 6, I will talk about the monitoring of the growth of particles during crystallization and aggregation processes. So first of all, I will show you a crystallization process in which ibuprofen will crystallize from solution by antisolvent crystallization. So I will start with a saturated solution of ibuprofen into propanol, and by adding the antisolvent, that in this case is water, the solubility of ibuprofen will decrease, and then it will start nucleating and growing. In this experiment that I'm going to show you in the lab, I will use water as antisolvent containing some 80 to prevent the agglomeration of particles, and I will use a solvent to antisolvent ratio of 1:3. After that, I will perform some extra experiment using different solvent to antisolvent ratios to see the differences in the different processes. So before moving to the lab, I want to tell you the things that are going to happen during this crystallization process. So first of all, during the crystallization, the solute will go from solution to solid state. And this process is called the supersaturation. So we want to track this process using the NanoFlowSizer, and we can do that looking at the backscatter intensity. So as more material is going to solid state, the intensity will increase. But also during the supersaturation, there will be a nucleation process, that is the appearance of new particles in suspension. So this nucleation process is more predominant in the first stages of crystallization, when the supersaturation level in solution is high. The second process that is going to happen is the growth of particles. So this growth of particles is more predominant in the last stages of crystallization. So this means that at the end of the crystallization, most of the solute is already in solid state, and the supersaturation in solution is low, and this will make the growth of the particles faster. But generally, in any crystallization process, we will see both things, nucleation and growth happening at the same time. So at the beginning of the process, we will probably see more nucleation, but there will be a point in which new particles will appear, and the ones that are already there will start growing. As you can see in this diagram. So after the crystallization process, I will also do some aggregation experiments in which I will use a suspension of silica, and by adding a salt, the silica particles will start agglomerating. So in this case, I will use silica particles with a particle size of 100 nanometers, and I will use a solution containing sodium chloride with a concentration of 100 millimolar. So these are the experiments that we are going to perform in the lab. So now we can move there and see everything at real time.
3, 2, 1, go!
Okay, I think at this stage we are close to the final experiments with the static vial module. I think one of the interesting applications that you will talk about or show to us is particle growth in a static suspension. So the crystallization, you will show us something about it, and also about particle aggregation and how to monitor that in real time.
Yeah.
Okay.
Okay, so here we have the materials for the crystallization experiment. So in this flask we have ibuprofen that is dissolved in 2-propanol. So this solution is saturated, and what we are going to do is to put water with twin, and by adding water you decrease the solubility of the system and the ibuprofen will start crystallizing. So I'm going to show one experiment in which I will use a ratio of 1:3 of ibuprofen in IPA to water. So then I will show in the slides other examples in which I use different ratios, and also I use water without twin to see how ibuprofen aggregates during the crystallization.
Because then it actually shows that it's really valuable for studying this type of mechanisms.
Yeah.
As long as it can do, of course, the real-time particle sizing.
Exactly. So we can see now that after adding the anti-solvent, there are already some particles appearing in solution. So I'm going to put it in the static model, and now we are going to monitor how the nucleation and growth of particles is occurring.
Okay.
Yes, so we can see now the first time points in which you can see already particles appearing. And we can already see some growth of particles, and now it's more obvious. So we can have information about the particle size distribution, and we first see here a small peak that is probably due to nucleation. So there are new particles appearing in solution, and then we can also see that this peak here is also moving to the right, but it means that the particles that are present in solution, they are also growing. And you can also see that in the increase in the zeta average. So this process is going to take approximately 20 minutes. So we can leave it running and see how it evolves over time, and then check the results after.
Yeah, sounds good. And I think it's really nice feature that you actually can monitor it directly, maybe more related to the set average increase, but in the end you can always reprocess the data also for particle size distributions. Actually what happens for every measurement, all the data is available for every measurement and stored.
Yes, yes. Okay. So yeah, I can also show you the place where the data is stored. So we have some Excel files where you can see all the data points with the intensity, particle size distribution.
Okay. Suppose that you have a much faster crystallization process or other particle growth mechanism. Would it be possible to even screen it at larger speeds?
Yeah, you can do that. So if you want to take more data points and do the experiment faster, you can change the acquisition settings in a way that you can perform faster measurements and monitor the growth in a really small period of time.
Okay. Is it also possible, because I think for the end result it's acquisition time for the measurement,
yes,
and also processing time for, let's say, calculating the results
yes,
before they are on screen. But if I'm correct, you can also separate the
exactly,
processing part and focus on only acquisition, but then you lose the, let's say, the real-time information. But afterwards in reprocessing you can actually have a detailed look.
Exactly.
Okay.
Yeah.
So even for fast processes, relatively fast processes on a more or less second scale, you can actually do quite some measurements and study the dynamics.
Yeah, exactly.
Yeah, nice. Okay, so now we are back, and I
Yes.
already can see in the file that it's a bit more turbid than
Yeah.
you started, so that's a good sign. And
Exactly.
there are much more data points on the screen as well.
Yes, so in the screen we can see now how the particle size have been growing during these 20 minutes. So in the top right graph, you can see the particle size increase over time and also the PDI. So you can see that it went from 20 nanometers at the beginning of the process going up to 500 nanometers after 20 minutes. And also you can see that now the particle size distribution only shows one peak, and also some bigger particles from 1,000 nanometers. This means that now, probably at this point of the process, there is only growth of the particles, and we lost this peak at 10 nanometers that is related to the nucleation and the appearance of new particles. So we can be sure that at this point it's mainly growth, and probably we are close to the end.
Okay. And the 1 micron, or let's say larger, small peak you see there, have you any idea where that's coming from?
It's probably either growth of the particles, because they can grow quite big, or agglomeration, because ibuprofen tends to agglomerate.
Okay. And actually, is it possible to see a difference between the agglomeration and particle growth?
Yes, so if we look at the data of the intensity and the back scatter intensity, we can have more information about how the solution has been desupersaturating over time, and then we can reprocess the data and get more information about the nucleation and growth.
Okay. I guess we will show more of that in the slides after the session.
Exactly.
Thank you. Okay, so we have seen now the crystallization part, and in contrast to crystallization, we also want to show aggregation.
Yeah.
And I guess the main difference is that the concentration of the material is not increasing in aggregating mechanisms,
Yeah,
in contrast to the crystallization.
exactly.
So after the session, you will explain the results and actually how you can see the difference in the software or in the signals that are obtained.
Yeah.
But now we will have a closer look to the aggregation
Yeah.
experiment and how to monitor the real time.
Yeah, exactly.
Okay.
So here we have a vial that contains silica with particles that are 100 nanometers. So what I'm going to do is to put some salt into the suspension, so then the particles will start aggregating. So first I'm going to put the vial in the NanoFlowSizer, and I'm going to do a measurement of the particle size right now before adding the salt. So we can see here in the screen that the particle size is 100. That is what we expected. And now let's see what happens when I add the salt.
And I guess the salt concentration also
Yeah.
defines how fast the aggregation will
Yeah.
occur, etc. So
Exactly. So now I'm using 0.1 molar of NaCl, but if I increase the concentration, it will go faster. So as you have said, the main difference between this and the crystallization is that at this moment we already have some particles in suspension. So it's measuring at the beginning some particles, but in the crystallization at the beginning there was a clear solution with no particles, and then over time more particles were appearing in solution, increasing the intensity. But in this case, the intensity is going to be constant during the whole experiment, and the only thing that is going to happen is an increase in the particle size.
Yeah.
So
in the screen we now see sometimes a sort of a red alert,
Yeah.
I saw the first alert that this signal is somewhat unstable.
Yeah.
But I think that might be due to heading
exactly.
some other stuff, and that there's lots going on in the signal itself, and then actually you get a warning that something is not okay.
Yeah.
And in the screen it's marked as a cross instead of a let's say spherical dot.
Yeah.
That actually represents good measure.
Yeah.
Or a reliable measure.
Yeah. So every time that there is a warning, you will show the cross in the screen. But now you can see that the data is quite stable, so we have reliable data. And we can already see that the particle size went from 100 nanometers to 127. And we are going to take more data points for maybe half an hour or a bit longer to see how this looks like at the end.
Yeah. So in the end, let's say the full picture of how the particles were increased.
Yeah.
We can show afterwards in the slides.
Exactly.
Okay. And then based on the backscattering intensity of the signal, you can actually see the difference between aggregation and particle growth.
Yes.
And a bit towards the difference between the effect where the concentration increases or not.
Exactly.
Yeah. Okay. Yeah, that would be nice. Okay.
So you have just seen some experiments in the lab, and after that I have reprocessed all the data, and now I'm going to show you some of the results in the following slides. So I will start with the crystallization experiments. Here in this graph you can see the intensity and the particle size as a function of the time. So the blue dots represent the supersaturation, and this means that as the intensity increases, more solute is going from solution to suspension, and this causes the supersaturation. And on the other hand, we can see in the orange dots the growth of particles. As I wanted to have a deeper understanding of what was happening in the process, I have represented the intensity as a function of the size. So we can divide the graph in two. The first half corresponds to the beginning of the process, and we can see a quite pronounced slope. That means that the solution is supersaturating quite fast, and we can see this by the high increase in the backscattering intensity. We can also see that there is an increase in the particle size, growing from 200 to 350 nanometers. In this first stage of crystallization, the nucleation is predominant. However, there is still some growth occurring in the particles. And we can see this in the particle size distribution graph on the right hand side. So we can see that at 1 minute and 5 minutes there is a peak at 10 nanometers that is probably related to the nucleation of new particles. And there is also a peak at around 200 nanometers that is related to the growth of the particles that are already in suspension. On the second half of the graph, we can see that this slope is less pronounced, and this means that the supersaturation rate is slowing down, and this is related to a lower concentration of solute in the solvent. So in this second part of the crystallization, the supersaturation level is slower, and thus the nucleation rate is also slowing down. So in this second half of the process, we expect just growth of particles, and the nucleation of particles won't be visible in the graphs. So we can see this in the particle size distribution graph shown at the top of the slide. We can see that after 17 and 25 minutes, there is no peak at 10 nanometers. That means that the nucleation is probably not occurring anymore, and all the solute that is going from the solvent to solid state is used for the growth of the particles. So the experiment that I have performed in the lab was shown in the previous slides, but now I want to show you a comparison of different crystallization processes using different solvent to antisolvent ratios, and also using water in the absence of twin to see if there is any agglomeration of ibuprofen particles. So we can see, first of all, that in the experiments in which twin was not used, the particles grow faster, and this is probably related to the agglomeration of the particles. Additionally, we can see that as I increase the antisolvent to solvent ratio, and thus the driving force for the crystallization, I enhanced nucleation and I created small particles. So up to here, I have shown crystallization experiments performed in a vial. But what I want to show you in this slide is that we are able to monitor the synthesis and crystallization also in flow. So this is a synthesis of titanium dioxide in which we monitor the particle size using our microflow cell. So the synthesis was performed in a round bottom flask, and the solution was pumped into the microflow cell where the particle size was measured at different time points. In this case, we used different concentrations of salt to see the differences in the different syntheses, and we can see in the graph on the right how the particles were growing and also the differences in the different syntheses. So finishing with the results of the crystallization experiments, now I want to show you the results of the aggregation of silica particles. So here in this graph we can see both the intensity and the particle size at different time points. So in this case, as the solids were already in suspension, there is no change in the backscatter intensity, being constant during the whole process. However, after salt addition, that it was performed after a few seconds, we can clearly see an increase in the particle size going from 100 to 150 in 10 minutes. In this slide, I want to compare the backscatter intensity obtained during the crystallization process and the aggregation experiment. So we can see that during the crystallization, as there was an increase in the concentration of solids in suspension, there is also an increase in the backscatter intensity. However, for the aggregation experiment, in which the solids were already in suspension, the backscatter intensity was maintained constant during the whole process. So what are the benefits of using the NanoFlowSizer for research and development? So first of all, you can have a lot of understanding of the dynamics of your process. And this is because you are able to have data in less than 10 seconds and at real time. Additionally, apart of knowing the size, you can also have information about how much solid is going to suspension. And because of that, you can have a better understanding of the nucleation and growth mechanisms, especially for crystallization at the beginning of your process. And finally, you can also have a rapid insight in the formulation and process parameters.
So, I hope you enjoyed the entire session, and with this last part of the crystallization that we saw, we want to end this demonstration event. We would certainly like to invite you to reach out to us if you have additional questions or you need more information about the system. So on behalf of the team, I would say goodbye, and we hopefully see you later.
Bye.
Bye-bye.